Welcome to Method Development in Gas Chromatography. So there are many different parameters available to us in gas chromatography. So how do we decide which to use? The general approach should be to decide upon the goal of the analysis, and then the sample preparation, and then the detector, and then the column, and then the injection method. So let's look at the goal of the analysis. What exactly is required from the analysis? Do we need qualitative identification of the components in a mixture? Do we need high-resolution separation of all of our components? Or do we only need high-resolution separation of the components in a portion of our chromatogram? Can resolution be sacrificed in order to decrease the analysis time? Do we need quantitative measurements of the components in our mixture? Do you need high precision? Are the analytes present in high enough concentration? Or do you need pre-concentration or a more sensitive detector? How much can the analysis cost? So each of these factors will influence the trade-offs necessary in selecting the method to be used for the analysis. The best way to improve the chromatographic separation of components in a mixture is to use sample preparation to remove some uninteresting solutes before chromatography even begins. That is, clean up the sample before it even hits the column. To do this, we can use solid phase microextraction, stir-bar sorptive extraction, purge and trap, thermal desorption, solvent extraction, so liquid extraction, supercritical fluid extraction, solid phase extraction, and note that solvent extraction, so liquid extraction, supercritical fluid extraction, and solid phase extraction are all discussed in detail in Chapter 27. In the absence of proper sample preparation, the chromatogram may contain a broad forest of unresolved peaks, and non-volatile substances will ruin our chromatography column. So next we need to look at the detector. The questions we need to ask when choosing our detector are, do you need information about everything in the sample? Or do you need only information about one element or class of compounds in the sample? A mass spectrometer can provide information about everything in the sample. A flame ionization detector will only respond to hydrocarbons. The sample must contain at least 10 parts per million of each analyte if we're using split injection. The thermal conductivity detector will respond to all of our analytes, but it isn't very sensitive. The electron capture detector is good for halogen-containing compounds, nitriles, nitro compounds, and conjugated carbonyls. The sample should contain at least 100 parts per billion of each analyte if using split injection. The photoionization detector is good for aromatic compounds and unsaturated hydrocarbons. The nitrogen phosphorus detector is especially good at detecting nitrogen and phosphorus compounds. It will also detect our hydrocarbons, although it is not nearly as sensitive to hydrocarbons as it is to nitrogen and phosphorus. An infrared detector can be used to provide some structural information to us, but it is not sensitive enough for high-resolution, narrow, open tubular columns. So next we select the column. We have a few parameters for the column, including the identity of the stationary phase, the thickness of the stationary phase, the column diameter, and the column length. A nonpolar stationary phase is the most generally useful to us. An intermediate polarity stationary phase will handle most analyses that our nonpolar column can't handle. And for highly polar solutes, then a highly polar stationary phase might be necessary. For separating optical isomers or closely related geometric isomers, a special stationary phase will be required. Table 23.6 shows the advantages and disadvantages of various column diameter and stationary phase thickness combinations. For example, with a thin film narrow bore column, we've got high resolution that's useful for trace analysis. We've got fast separation, low temperatures, and we can elute high boiling point compounds. On the other hand, we've got a low capacity, it requires a high sensitivity detector, and we have some surface activity of exposed silica. With a thick film, narrow bore, we have a higher capacity than in the thin film. We have good resolution. It's relatively easy to use. It retains volatile compounds, and it's good for mass spectrometry. On the other hand, we've got moderate resolution there's a long retention time for high boiling point compounds. Over here, we've got a thick film wide bore, so we have a very high capacity here. It's good for thermal conductivity and infrared detectors. We've got a simple injection technique, but we've got a low resolution and long retention time for high boiling point compounds. So if a column meets most of your requirements but provides insufficient resolution, a narrower column of the same type can be used. We can increase the resolution by increasing the length of the column. Doubling the length of the column increases the resolution by √2. However, doubling the column length will also double the retention time, and thus increasing the column length is not the best way to improve resolution. Instead, a narrower column should be used because it increases the resolution without increasing the retention time. Alternately, a different stationary phase may provide a better resolution for the components of interest to us. To decrease the analysis time without sacrificing resolution, a shorter, narrower column can be chosen. Alternately, the carrier gas can be changed from helium to hydrogen and increasing the flow rate by a factor of 1.5 to 2. Figure 23-28 shows the approximate upper and lower analyte mass limits for different columns and detectors. So we have a stationary phase thickness here of ranging from 0.1 microns to 5.0 microns. And if you have some thickness in between there, then the value will be in between that. So down here we've got the injected solute mass, and note that this is a logarithmic scale here. And we have some various column parameters. The column diameter here ranging from 100 microns up to 530 microns. And we have some various detectors down here and the ranges at which those are useful at. So you can see that the mass spectrometer in selected ion mode is more sensitive than the mass spectrometer in scanning mode. The electron capture detector is very sensitive. The thermal conductivity detector is not very sensitive. So that brings us now to the injection method. We have 3 injection techniques: split injection, splitless injection, and on-column injection. The split injection is best for high analyte concentrations or gas analysis. However, quantitative analysis is poor, less volatile components can be lost during injection, and temperature-sensitive analytes may decompose. Splitless injection is best for low analyte concentrations. The resolution is high, but quantitative analysis is relatively poor because the less volatile components can be lost during injection. The solvent trapping or cold trapping is required because the sample is injected slowly. And thus, splitless injection cannot be used with isothermal chromatography. On-column injection is best for quantitative analysis and temperature-sensitive compounds. However, it is inherently a low-resolution technique because it requires a column diameter of at least 0.2 millimeters. That was method development in gas chromatography.